All right, guys, here we go. An example problem of torque. The third example problem. It's a pretty interesting one. All right, let's see what we got here. First thing you want to recognize is you may want to try to do this with some of the forces. First, you got the weight of the plank, the weight of the man. Both of those things are down, right? So if you were to consider some of these things, you've got like the weight of the plank down, you've got the weight of the man down. That's not to scale. The weight of the man is much greater. And then you've got the force of tension from rope 1 and the tension of rope 2, all those forces there. If you were to try to do some of the forces equals MA. And somewhere in here, the problem should read that everything is at rest, not accelerating or rotating. It's held still. Okay. You'd want to say like all the forces up equal the forces down. They're balanced. So if you were to try to come up with that, you'd say Fg of the man plus the Fg of the plank equals tension 1 plus tension 2. You can figure out the weight of the man. The weight of the man is just about, we'll use 10 as a nice simple number for the acceleration due to gravity, is 500 newtons. And the weight of the plank is going to be 50 newtons. So you get 550 newtons equals T1 plus T2, but there's no way to separate those T1s and T2s. So when you do it this way, you end up with one equation, but two unknowns. You're stuck. You can't go anyplace. So there is another way to solve the problem, and that is with torque. We can do this. It's really pretty easy. If we say the sum of the torques are 0, that would mean that the torque produced by the first force plus the torque of the second force plus the torque of the third force plus the torque of the fourth force all somehow make 0. Okay? Now, the same forces apply. We're going to be dealing with the same forces. We'll call we'll say the rope 1. That could be one rope. That could be force 1. The man, his weight, we can make that the second force. The plank, the weight of the plank itself. Weight of the plank, weight of the man, and then T2. These forces all can sum to be 0. Each one of these forces is going to cause some rotation, but we have to choose a pivot point. I should have started with that. We have to choose a pivot point. That's important. Choose pivot point. Torque, I'll show you why I'm going to choose probably this spot right here as my pivot point. I'll explain why in a moment. But torque is force times your distance from that, right? FR sine theta, F1 sine theta, F2R sine theta. Here, all these thetas are going to be 90 degrees, so it's going to be 1, but I'll write it on there. F3R sine theta and F4R sine theta. Any force that causes a rotation in the clockwise direction will be considered negative. Any force that causes rotation in the counterclockwise direction would be considered positive. So that's convention, right? Counterclockwise, positive, clockwise is negative. Should remember that. So if we make this location here our pivot point and say which way these things are moving, well then T1 is R, T1R is 0. So you could get T1 times 0 times the sine of 90, which is 1, which is going to go to 0. The weight of the guy here is going to cause the plank to swing down and in a clockwise pattern, so we'll make that negative. The weight of the guy we said was 500 newtons. He is 2 meters away. Again, times 1 sine of 90. The weight of the plank itself is also cause it to rotate. Right, if this was the hinge point, that would cause rotation that way. That would cause rotation that way. So that's why those things are negative. The weight of the plank itself is 50 newtons. And this is 5 meters away. Again, sine of 90 is 1, so that's easy. That's F3. F4 would be T2. T2 would, if you didn't have these other things, T2 would cause it to rotate this way. And that would be counterclockwise. So we'll call that one positive. And we don't know what T2 is, but T2 times how far away is T2 from the pivot point? Not all 10 meters, it's 1 meter in, only 9 meters in, times 9 meters, again, times 1. What's nice here is making that your pivot point, one of your unknowns goes away, so you get 0 minus 1,000, 500 times 2 is 1,000, Newton meters, minus 50 times 5 is 250. 250 Newton meters plus T2 times 9 meters. All this equals 0. That's the sum of the torques. Sum of torque is 0. So we get 0 equals negative 1,250 Newton meters plus T2 times 9 meters. Bring this over there. So we get positive 1,250 Newton meters equals T2 times 9 meters. Now we can figure out that T2 is equal to 1,250 divided by 9. Right? Divide both sides by 9. Divide this by 9. Divide this by 9 meters. Divide this by 9 meters. 1,250 divided by 9 gives you 139 meters. That is very, very important. Now we can take that and bring that up into here. We had 550 newtons was equal to T1 plus T2. Now we know T2, 550 newtons equals T1 plus 139 newtons. So T1 is equal to 550 newtons minus 139 newtons, or 411. T1 is equal to 411 newtons. And that is the way to solve the problem. 411. That should make sense if you think about it. If you have this big force over here on the left-hand side of the plank, T1 is supporting more of the weight. T2 shouldn't have to support as much. More of the mass, the center of mass of this thing, is over here on the left. So rope 1 is supporting more of the weight than rope 2. That agrees. One other thing that you should know about, there is a normal force. It exists, right? There definitely would be a normal force between the man and the board, right? You would think there would be a normal force there. But because it's sort of internal and not acting on the system, it doesn't produce any torque. Okay? It's coming from the plank itself, but the plank itself can't make itself move. It's an internal force. It doesn't act on the system externally. It doesn't act on anything. So it can't make it rotate. It would produce no torque. So it's not part of the torque problem. But the rope pulling up on the plank, T1 or T2, the weight of the man pushing down on the plank, the weight of the plank itself, right? That's the earth pulling the plank, not the earth pulling the plank would cause it to rotate. But the normal force, the support of the man pushing up on the man, it's on the man, it's not on the plank. It doesn't cause the plank to rotate. So it doesn't exist, or it doesn't get factored into our math here. All right, I hope that makes sense. We're going to do a bunch of these. But again, when you go to some of the forces, you get stuck with one equation, two unknowns. When you go to some of the torques, because you can make one of the unknowns vanish, you could have solved this problem making the pivot point over here. Your signs would have been reversed, but the math would work out the same. You just want to make sure that one of your unknowns is 0 meters away from your pivot point. All right, those are the key pieces to solve that problem.